Hey guys, I'm Josh Clark, and I thought we were kind of quicker today, so it's going to be kind of annoying, but I'm presenting the first law of thermodynamics. As y'all seen like the previous talks, it comes up a lot, especially in this class. Shout out to Dr. Guo, he taught me thermo stuff. So some objectives for today. First one, just to make sure y'all are in the right classroom, I'm going to review what thermodynamics is. Pretty simple one. After that, I'm going to give y'all some theory behind the first law, explain the equation, why it's made, how we use it. After that, some pretty simple processes that affect the first law and that we use with the first law. And then two simple applications using the first law to demonstrate everything. And just for some humor, because we are talking about thermodynamics. So, what is thermodynamics? Thermodynamics is the science of relation between four things. Can anybody tell me one of those things? Anybody?
Energy.
Energy. All right, there's one. All right, so you got heat, work, temperature, and not least but last, energy. All right. So next thing, so we're getting into the first law now. We've already kind of talked about it briefly, but the first law is often called the conservation of energy law, which everybody can kind of conclude what that means. This means that heat energy cannot be created or destroyed. It can, however, be transferred from one location to another and converted to and from other forms of energy. So this is the basic equation. As you see, du, which is the change in internal energy, is equal to the heat that's added to the system minus the work done by the system. So there's two manipulations of this formula. You'll see that du equals q plus w, and they take into sign convention, but how we were taught to do q minus w. So talking about processes now, isothermal. What's isothermal? Anybody?
No change in temperature.
No change in temperature, right? So iso means constant, thermal means temperature. So isothermal process is one where the temperature does not change. So if the temperature is not changing, the internal energy will not change at all. So that term in our first law equation is going to go to 0. So our new equation is going to look just like this. Q is equal to W. So the work done is equal to the heat that's put in. I put a pretty simple application of an isothermal process. A lot of times with a movable piston, they'll put a constant heat at the bottom. So either way they move up and down, the pressure and stuff will change, but the heat is going to stay the same. And then here's a simple PV curve of how it changes with the piston. Next one, adiabatic. Adiabatic process is one where there's no heat flow into or out of the system. So that's the Q term. So Q goes to 0, and all changes in our internal energy are dependent on the work done on the system. So our new formula becomes the change in internal energy equal to negative work. So the internal energy is inversely proportional to the work done on the system. Here's another PV diagram. I know y'all are familiar with that. So next one, isobaric process. This occurs when there is constant pressure. Okay? So if we recall, work is the relation of pressure times the change of volume. So if we substitute this into our first law equation, du equals q minus p delta v. That's our new equation. Okay? And that's what your PV diagram is going to look like when you have an isobaric. Does anybody know how to find the work under a PV diagram with a constant pressure line? It's going to be the area of the curve. So you're gonna take A and B, and you're just going to take the area of, it's going to be the area of a rectangle. Next process, isovolumetric. There's a few names for this, isochloric, but I'm using isovolumetric. So the only one left, this is when you have constant volume. As stated previously, work is dependent on the volume change. So if we don't have any volume change, what do you think is going to happen? Our work's going to go to 0. So our new equation becomes Q equals delta U. So in isobaric how it was inversely proportional. This one's directly proportional to the heat put in and your internal energy. And that's what your isovolumetric PV diagram looks like. So, little example to reiterate. This is my Q control volume that I made in Excel. So the problem saying is a steel ball weighing 5 kilogram rolls horizontally with the speed of 10 meters per second. If on an incline, how high will it be when it comes to rest? So from the controlling volume of the steel ball, we see that delta U equals Q minus W. That's the equation we first started with. Then we're going to break it up into states, okay? Because you're coming to rest and you're then moving. So you got U2 minus U1 equals Q12 minus W12. After that, these two direct substitutions where U2 and U1 and little U2 equals little U1, you come out with this. And if you see Z2 minus Z1 is the height factor that we're looking for. So after plugging in the numbers that we were given, we're going to find Z2 minus Z1 equal to 5.1 meters, okay? And then in the last example, just for a simple one to show you, is if you got 60 joules of work done on a gas and the gas loses 150 joules to heat, what's the change in DU internal energy? So you're losing 150 and you're gaining 60. So your change in total internal energy is 90 joules lost, okay? And that is the end of my presentation.